Hey guys, I welcome you all to this informative session by Create Learning. So, Naïve Bayes classifier is built on Bayes' theorem and is one of the oldest approaches for classification problems. Naïve Bayes can be used for sentiment analysis, weather prediction, medical diagnosis, and multiple other things. So, understanding the importance of Naïve Bayes, we have come for this comprehensive tutorial. The session will be taken by Professor Mukesh, who has over 20 years of industry experience in market research, project management, and data science. Now, before we start off with the session, I'd like to inform you that we'll be coming up with a series of high quality tutorials on artificial intelligence, data science, and computer vision. So, please do subscribe to Greek Learning's YouTube channel and click on the bell icon so that you get a notification of our upcoming videos. So, in this tutorial, we'll start by understanding the core concepts of Naïve Bayes and then we'll implement a demo with Scikit-learn. So, let's start off with the session.
This model, this algorithm is based on the Bayes theorem. It is used for classification. Again, it uses probability values to decide which class a test point belongs to. This is the only algorithm which gets this term associated with it called naive. The term naive is not a very good thing to be associated with. Okay, but this algorithm is the only one which gets associated with that. Very unfortunate, because all algorithms are naive as per this definition. The reason why it's called naive is this algorithm assumes that all the variables that you're going to use to build the models, those variables are independent of one another. The independence assumption is often violated. We already discussed this. But then this is true for all the algorithms. It's called naive due to the assumption that the features in the data set are mutually independent. They don't interact with each other. But that's what every algorithm does. So this is the only one which gets the cap, the hat, whatever you call it. But the beauty of this algorithm is, what this algorithm says is, howsoever weak predictors your features may be, don't drop them. Consider them. Take into account the information given by each feature and build your model based on probabilities. So it doesn't advocate you from dropping any of the features. However significant the overlap might be, use them. That's what this algorithm says. To understand this algorithm, we have to understand what is probability, we have to understand what is joint probability, and we have to understand what is conditional probability, three of them. So let's quickly start. What is a probability? How do you define probabilities? Okay, chances of some event occurring. So in the definition, you have an event, and then you have something called chances. What is chances? How do you find that out? How do you find the chances of something happening? So what involves the experiment? What is there in the experiment? Trials and proportion, right? So if I ask you, what is the probability that today it will rain? And you might be surprised, just a week or 10 days ago, there was news in the web where in Kerala there was snowfall. Have you seen that? In Kerala there's a hilly, what do you call, hill spot? Munnar, right? There they had snowfall and the temperature was -3, right? So such events can happen. So if I ask you, what is the probability that today it's going to rain at 5 o'clock? Why did you say 0? Who said 0? Yeah, why 0?
Sunny.
So
I don't see any clouds.
So
Never happened. Check my
don't check the weather. Just talk. So what you've done is you've taken your past experience into account. On this particular date, month of January, almost middle of January, how many times in the past did I see rain? That ratio, how many times you saw this event of interest versus your past records, the number of trials. This ratio is called frequentist approach to probability. So the probability is a ratio where it's a ratio of the events of interest to you, how many times they have occurred, out of the total number of trials, how many times the event could have occurred. That is a ratio called probability values. Did you know that probability values can be calculated in another way? Have you done Poisson distribution in statistics, Poisson distribution, very convoluted formula there. If given the state I am in, what is the probability that I'll be in a different state, the next state? That is a function of how many ways you can reach that state. Okay, so that is another way of finding probability. We are going to use the previous definition of probability, which is based on frequencies, ratios. Okay. Now that you know what is probability, the next thing you need to know is what is joint probability. Joint probability is probability of multiple events occurring together. Okay. So what is the probability of, if I give you a deck of cards and I ask you to pull a card out of it, and I ask you what is the probability that this card is going to be a red king?
1 by 52. 1 by 52 is red.
No, you never played cards.
2 by 2
You have 52 cards. Red king.
2 by 2.
Red king is 2 by 52. So there are two colors, red and black, 52 cards. So 52 cards, you have two red kings, hearts and diamonds. So the probability of this joint event of red king is, red is 1, king is 1, the probability is 2 by 52. Alright? Now when you're pulling out the card, somehow you come to know that it is a red card. Somehow you come to know it's a red card. Now what is the probability this is a red king? Now you know it's a red card. So your scope is now limited to only red cards. 2 by 26. 2 by 26 is 1 by 13. So you have taken into account an evidence, an information that you captured that it is a red card. The moment you get that information, you recalibrate your probability of red king. That concept of recalibrating your probabilities based on the information that you're gathering, that concept is called Bayes' theorem. So what Mr. Bayesian said is, start with some probability, the default probability values, but keep on recalibrating those probabilities the moment more and more information comes to you. Howsoever the information may be, howsoever weak the information may be, don't ignore any information and recalibrate your probabilities. That is the philosophy or reasoning behind this Bayesian theorem, Bayesian models. Are you all okay? So for this, to understand this, we need to know probability, joint probability, and your what is conditional probabilities. Conditional probabilities, what is the probability of king given it's red? We know it's already red card. So now only the event left to happen is king. So what is the probability that this card will be a king given it's red? That concept, which you call 2 by 26, that concept is called conditional probability. So we started by joint probability. What is the probability it's a red king? Because we didn't have any information. It was 2 by 52. The moment we came to know it's a red, then we switched to conditional probability. What is the probability is king given it's red? Right? Conditional probability is invalid if joint probability is 0. If probability of two events occurring together is 0, we don't talk about conditional probability. What is the probability of drawing a green king? There is no green king possibility. So don't even talk about conditional probabilities. So we talk about conditional probability only when we have joint probability greater than 0. All right. So let's see how all this was put into build a model. We already discussed this. What is probability? What is joint probability and what is conditional probability? We already discussed this. So I'm going to jump these slides. This is the model. I'm sure you would have seen this formula. Looks very familiar. Wow, man! You should put it on some kind of board and put it on. Looks so like you're going to launch some rocket. It's very easy. Okay, so what I'm going to do is I'm going to jump all this slide back. I'm going to explain with some animations. This blue box represents all the flight information I have captured from my experience. All the 100% flights which I have taken, I'm representing it by blue box. The dimensions of the box are inconsequential, they don't matter. When I look at my past data about the flights which I have taken, I notice that 20% of the time there was flight delay, 80% of the time the flight was on schedule. In mathematics in school, you would have done this as Venn diagrams. Okay. I also noticed from my past information, past data, that 5% of the time there was fog at the airport. Now it's natural for us to quickly link fog with the flight delay. Don't do that. We are not here to say that the flight delay was because of fog or fog was because of flight delay. We're not here to establish that link. Naïve Bayes algorithm assumes that these two events are independent of each other. Whatever the reality may be, the algorithm assumes these two events are independent, they have nothing to do with each other. Okay, but we know through our experience that they are not really independent. But the algorithm assumes they are independent. Okay, and we know that if I mark this as flight delay, no fog, this is fog but no flight delay, this crescent. This is the case where flight delay and fog occurred together. That does not mean flight delay led to fog or fog led to flight delay. We don't know. We are assuming that they are independent. What's going to happen is, the lesser the overlap, more unlikely they are linked. The more the overlap, more likely the two events are linked. They influence each other. But I repeat, we are not here to establish any causal relationships. We are assuming that the two are independent.
So you mean to say, suppose there is a strong relationship from our intuition that for a particular use case, we found that there could be a strong relation, then we should not use Naïve Bayes in that case.
Correct, we should not use Naïve Bayes. All algorithms are like that. All algorithms show you the independent variables orthogonal to each other. That means they are independent of each other. Mathematically, when two things are independent of each other, they're shown at 90 degrees. If two attributes are very strongly influencing each other, you have to replace them with one synthetic dimension, PCA, or drop one. You have to do that. Same thing applies here also. Shall we move on? Okay, now look at this. Let's look at this region closely. This region is the intersection region, okay? Probability of flight delay and fog, the two events, the joint probability, okay? Now I told you I want conditional probability. Now that I'm seeing fog at the airport, now that the card is a red card, what is the probability there'll be flight delay? Now that it's a red card, what is the probability it's a king? So what happened? Your base, which was earlier 52, it shrank to 26. Same way here. Now that I'm seeing fog at the airport, what is the probability the flight will get delayed? So the base becomes fog. And the numerator is this area. So probability of flight delay given fog, the conditional probability is this intersection area divided by the blue. So if this is red cards, this is red king, these are the other cards. So what is the probability of red king? It was 2 by 52. But now that I know it's a red card, that means this is not my base, this is my base. What is the probability it's a king? Numerator by denominator. All right, all of you okay? Okay. Let's move further. I'm going to write this equation on one side and play around with this equation a bit. Caution, be ready to slip. So P A condition B, this I'm showing it here as P A intersection P by PB. A intersection B by PB. All of you okay? Can I rewrite this equation and rewrite this equation 1 as P A condition B into PB is equal to PA intersection B. Can I do this? Can I do this? All of you okay? Okay. Look at this PA intersection B. Does it make any difference whether I write this as PA intersection B or PB intersection A? Does it make any difference? Okay. If P intersection B is this, then PB intersection A, where the numerator is changed and the denominator is changed, it becomes PB given A into PA. Okay? I take this expression and I put it over here. So this conditional probability becomes P intersection B is PB given A into PA divided by PB. This is your Bayesian model. I'll tell you what it means. This is all algebra, but let's understand what it means. What is the probability of a person being diabetic given the conditions? So this is the class diabetic, non-diabetic. These are the independent variables, the BP, the plasma, and all these things. So what is the probability a person is diabetic given the conditions? What Mr. Bayesian said is, instead of building models, go back to your data. From your data, pull out all those records where people were diabetic. How many of them had these conditions? This is called likelihood ratio. Go back to your data, from the data pull out all the diabetic cases, how many of them had this condition? So instead of building models, do this. Likelihood ratio. Multiply that with what is the probability of anybody in the population having diabetes? So this is my base probability. What is the probability is reigned today? 0% based on past experience, and this is that probability. Recalibrate this using this likelihood ratio. What is the probability of red king? 2 by 52. We modified that into 1 by 13. That is recalibration. That is what this numerator is doing. So this is called likelihood ratio. Prior knowledge, you already have knowledge about this ratio in the universe. And this is called evidence. I'm seeing this occurring. Given that it's a red, I'm seeing that occurring. This is evidence. So the argument which Mr. Bayes put is very simple. He did this 200 years ago. He said that instead of trying to build a model for this, go back into data, pull out all the cases which satisfy the condition, which are diabetic, belonging to that class. How many of them had this conditions which you're seeing today? That's all to this model. So this model, this is called likelihood. This is called prior. This is called evidence. And whatever you come out with, this is called posterior. And we do this in common sense. I'll give an experiment to you. Are you all ready? Yes. We actually use Naïve Bayes in our day-to-day life. Lakshmi, is it going to be male or female?
Lakshmi Kant is not.
Lakshmi is evidence now. Is going to male or female? So what you're doing is you're going back to the past. How many times you have come across this name where it was a female versus where it was a male? So you're pulling out all the past Lakshmis that you have in your mind. How many of them were males, females? In how many of that's Bayesian probability. I have a friend called Lakshmi Narayan Babu. And this one particular name I'll not forget because there was one class which I was supposed to attend and the class was being taken by Lakshmi. Every door I opened, there is a male standing there. Every door I opened, there was a male standing there. So it took me some time to understand that this guy's name was Lakshmi. So I did a wrong interpretation. Lakshmi means female, but there are people, males with name of Lakshmi. Right? So what you've done to answer this question is Bayesian probability. Right? So it all looks strange, but we all use it day to day life. Shall we move on? Okay. Any questions on this? Yeah, this one will give you that. That reminds me. Okay. So before I move on, when you read about these algorithms in books and articles, you need to be slightly careful. So let me explain what the problem is. So what happens is, what is the probability of A given B is equal to probability of B given A into P A by PB. All right. Many of the authors, okay, what is the probability of not A given B? So whatever this probability is, 1 minus P A given B. Okay. So this I can write it as, all of you understand what I'm doing? Probability of A given B, probability of king given red. What is the probability of not king given red? That's what we are doing here. So this I can write it as P B given A into P A by PB, which can be further written as PB by PB. Agreed? All of you okay? So whether you're finding probability of A given B or not A, I'll put it as like this, not A given B, both of them have in the denominator PB. So it is not PB which is going to decide whether this is going to be class A or class B. What is going to decide whether it's going to be class A or class B is the numerator. The numerator. If this crosses 0.5, he's going to belong to class A. If this crosses 0.5, he's going to belong to not class A. Get my point? So what decides your class is the numerator, not the denominator. Denominator is same in both. So many of the authors, they don't reflect this. They say that this is the Bayesian model. And you will keep wondering, where did the PB go? So the reason why they don't show PB is that it's the numerator which decides the class. However, in case you want not the classes but the probability values, then you'll have to divide the PB. All right? And the reason why they don't show PB, they often say that PB is a constant. What the hell? What do you mean by PB is a constant? PB is a constant. Some people say that since this is an evidence has already occurred, this is 1. Probability of an event which has already occurred is 1. So they use that argument also. But the argument is, mathematically, for classification, PB is not important, so it's not shown. All of you okay? Okay.
In this diabetes, so the PB of A is doesn't go in diabetes, what?
Given the evidence, given what you see.
And EA is already.
Sorry.
What is PA in this diabetes?
This is, anyway, how many people in the population are diabetic? Yeah. No, diabetic. Which symptoms we don't know. In the population, how many are diabetic? What percentage? That is this PA. How many are diabetic with these symptoms? Likelihood ratios. Okay. Now I'll go back to the slides which I jumped, or should I go forward? Just 1 second, let me check. Yeah, I'll go forward and then go backward. So I have a data set. This data set is 100 records. You see 100 in the bottom right. Total number of records is 100. Of this 100 records, 80 records no flight delay, 20 records flight delay. That's what I showed you in the Venn diagram. Okay. 20 times when there was flight delay, I noticed 4 times there was fog at the airport, 16 times no fog at the airport. This is that overlap between fog and flight. I also noticed that 80 times when there was no flight delay, 79 times there was no fog, 1 time there was fog. This is the same Venn diagram which you saw earlier. Okay, if you are getting confused, this area is no flight delay, no fog. This area is fog, no flight delay. This is one time which is occurring in my case. Yeah. This blue, the blue left out region is no flight delay. No flight delay and fog. This crescent which you see here is this one. No flight delay and fog is this. This is the crescent. Okay. We convert this into ratios. 4 by 20, 16 by 20, 1 by 80, 79 by 80. We convert into ratios, the likelihood ratios. Now, once you convert into ratios, you can use any permutation combination to find the probability. This is what we have seen earlier. Okay, you can put those ratios over here and you see the calculations. Okay, what I want to show you is I can extend this argument. I can extend this argument to include multiple parameters. Once again, I have only 100 records. 80 times no flight delay, 20 times flight delay. Okay, and these are the various events which I have captured from the past. These are my attributes. So 20 times when there was flight delay, 4 times there was fog at the airport, 10 times there was technical snag. Oh, what is this? Oh, this, okay. Yeah, 0 times there was pilot fatigue. Okay, so these are all my observations which I convert into likelihood ratios. Keep in mind, these don't have to total up to 20. They can be overlapping regions in the Venn diagrams. They don't have to total up to 20. What I mean is, in the Venn diagrams, these regions might be overlapping each other. Okay? So I convert everything into likelihood ratios. Now look at this. Probability that flight will be delayed, given that I am observing fog at the airport, but no technical snag reported. How do you find the probability that when I see these two events occurring? Use the formula, treat the event of flight delay as A and the combined event as B. So it's again probability of A given B. Okay, PA given B is nothing but probability of flight delay given these two conditions. You know how to handle this? It becomes PB given A into PA. You're going back into your records and seeing how many times flight delay happened, how many times these two events occurred together in that records. That is what this expression is.
So the likelihood is P B given A, right? That
Yeah,
the
likelihood
table,
ratio.
the table.
Correct, likelihood ratio. So P B given A, B is a compound event right now. So P given A is this. PA continues to be PA. That's nice. Who did that? Okay, divided by probability of B, PB. So you can form any permutation combination of these events and substitute into this equation over here, the likelihood ratios, and I'll tell you the probability. What is the probability of flight delay now that you're observing these events? So you can keep on recalibrating your probabilities. Forget flight delay. What is the probability of an intrusion, network intrusion, given that I'm seeing this IP, I'm seeing this login ID from this particular geographical location. So you keep on recalibrating your probability values. The moment you see such events in the log files, the moment the probability value crosses a threshold, you send your alarm. Right? But there is a problem. We have time, so we'll discuss the problem. What is the probability of flight delay given fog at the airport and say buffaloes grazing on the runway? I don't have any data about buffaloes grazing on the runway. So this algorithm will give you the probability is 0. Okay, this comes from experience. Earlier in Delhi, we used to have Palam Airport. Palam Airport had no boundary. So you can see a lot of buffaloes coming from the villages and grazing sitting on the runway, right? So what is the probability of flight delay given fog and buffalo at the runway? The algorithm will give you 0 because you don't have any such information with you. So for that we use something called Laplace smoothing factor. So Laplace smoothing factor sounds very hi-fi, but it's actually adding one small to the numerator, adding one small 0.0005, a very small number. You're free to add any number you like. This very small number prevents the numerator from becoming 0 when those rare events occur for which you don't have data. Okay? Since the event is very rare, we give it a very low value. There's a lot of technical discussions behind this, but this is called Laplace smoothing factor. By default, it's a very small value of 0.00005. Any outlier, any event comes in the test record, which you have never seen before. So at that time, the probability should not become 0. It's a probability very low value. That low value comes because numerator is very low. So any rare event for which you don't have any training data, when it occurs, this expression will become 0. But this will prevent it from the numerator from becoming 0. So the probability value will be conditional probability will be very low. Generally, it's a prefixed constant, but you can change it if you like. Any other question on this? Shall I go back to the slides which we jumped? Now those slides which earlier looked like hieroglyphics now will make sense to you. So this is where we jumped. Is it okay? So posterior probability is this, which you're trying to find out. Not prior. This is my likelihood ratios. It's also called conditional probability. I mean, this can also be called conditional probability, but this is posterior. This is likelihood. This is prior. This is my evidence. Some books, some authors will reflect it like this, but it means the same thing. So the class that will assign to a test record will be whether this numerator is greater or this numerator is greater than 0.5. That is called argmax. Okay, so whichever numerator is higher, accordingly the class will be assigned to the test label. So that is indicated by this. The technical name that we use for comparing the numerators are argmax. Which one is maximum, higher?
You mean whether PB is greater or PA is greater? That's what you mean?
Now, whether this numerator, and there was one more numerator here, right?
1 minus.
Oh, okay.
So let me rewrite the numerator here. So this is PB minus PE given B.
No, B given
Correct. It's opposite.
1 minus, no. So this will be 1 minus PA given B is this, given A into PA by PB. So what this will become PB, and this whole thing will become PB. So now argmax compares this with this, whichever is greater than 0.5, that class will be assigned to the test label. Then important thing, too much of words, but let me tell you in a brief way, because this algorithm assumes all these different events to be independent of each other, they don't influence each other. In probability theory, you would have seen when events are independent of each other, we multiply their probabilities. See, I told you. So when events are independent of each other, we multiply those events. Remember that in probability theory? So in the base, since the events are independent of each other, we multiply these events. What I mean by this is, look at this example. Look at this example. This is my numerator, this is my denominator. Probability of fog, no technical snag. Probability of fog, no pilot fatigue, no passenger delay. If you want to find all those things out, just take individual probabilities and multiply each other out. Right? I'm not showing multiple things over here, but you can just multiply the individual probabilities over here to find the PV. B is a condition. So in diabetic case, it was this represents blood pressure, it represents plasma, it represents something else. So I can say numerator, where I'm using it, what is the probability of your diabetes given blood pressure? What is the probability of diabetes given plasma into what is the probability of diabetes given this, that? So just multiply those events because they are independent events. That is what the numerator will become. Right? Same thing is shown. You will come across this expression. Don't get scared with this. This is what it means.
The same equation we will repeat for each of the.
Yeah, each of the attributes. Multiply.
Class.
Yeah, W is a class. Which class it belongs to? All right. There is actually a lot of depth and discussions on this Bayesian probabilities, which I'm assuming you're done in statistics. I'm going to move to the hands-on. Before I go into hands-on, advantages, disadvantages. Just like your logistic, it's very fast both in training and testing. K nearest neighbor is very fast in training but very slow in testing because it has to find so many distances to find the K nearest neighbors. Does well with noisy data is what you will see in many of these books and articles, but noisy data means there is a lot of jiggle in the universe from where you're taking the snapshots, which means 2 consecutive snapshots will have different distributions. Okay, so you have to take this with a pinch of salt. Any algorithm will find it difficult with noisy data sets. Requires few examples for training. Again, something which we need to actually take with a pinch of salt. As long as the few examples are a good representation of the universe, but otherwise no. We can convert our class into probabilities. Sometimes probability is useful. Predict underscore proba. So we make use of the probability, predict underscore proba, the probability values, to actually change the thresholds using binarized functions. Okay, we'll talk about that later. Biggest disadvantage is the assumption it makes, but then that is the assumption made by all the algorithms. When you have too many numerical variables, first it will convert these numerical variables into bins, boxes. Okay, it will categorize them, create bins, and then calculate the probabilities. People have said that the estimated probabilities, conditional probability, is usually less reliable. It's not reliable. That is true because these probabilities, assumption is the attributes are independent of each other. But because attributes are not independent, these probabilities have to be further jacked up. That is the same problem that you saw in p-values. Between MPG and horsepower, if there is a relationship and there's a p-value, why should that p-value change when you use, along with horsepower, the weight of the car also? Both the coefficients and the p-values for the horsepower change when you add some more dimensions to your analysis. That happens because of the collinearity between horsepower and the weight columns. So this is true for all the cases. Estimated probabilities are, so estimated coefficients are usually different from the coefficients in practice. If you come across a rare event, then the numerator can become 0, but we can handle this using that Laplace factor.
So one more regarding disadvantage. See, you are considering all the attributes. Say you have huge number of attributes. So will it be slightly slower these days because you are considering?
It will be relatively slower to less number of attributes. Yes, it will be, but it will not be visible to you. It will not be significantly different. However, you need to be aware of curse of dimensionality. You should be aware of curse of too many dimensions, too less records, then this any algorithm can end up in curse of dimensionality. Shall we try this on the Pima indents dataset? Okay. Before I proceed, in the UCI dataset, have you seen the UCI repository? To my knowledge, there are 512 datasets. Pretty rich source of data. I might cover in the class Pima diabetes datasets, but nothing prevents you from going and building these models on the bankdata.csv, where to predict defaulters versus non-defaulters. Just go ahead and practice this. Don't worry about the accuracy and all. How do you tweak the accuracy to a further higher up level? That will deal in feature engineering model tuning. But first thing that you should do is get used to the libraries that you need to call. Second thing you need to learn is the basic syntax of scikit-learn. Third thing, by the time you become comfortable with all these things, then we can go into model tuning. Okay, so that will bring in continuity in your, I know many of you are on jobs, you'll find it difficult for the continuity to be there. This is one way of ensuring continuity. Yes, sir.
Why the not suitable condition?
It's a ratio, so the ratios will have to be, first it will have to bind. Do you know that even decision tree does that? When you use it for classification, it has to bind. So if I have an attribute called plasma, it will bind first, equidistant bins will be created. So if you have too many numerical variables, it will take time to do that. But however, we will not see all these things because we have today modern computers which are very fast. Powerful. This algorithm was 200 years ago.
But the problem was with slowness, not with the accuracy.
No.
It was only with the performance.
Performance.
So decision also making of condition.
They are all under the hood. They are all related. Decision tree also creates based on entropy and Gini index, the homogeneity. That is another way of maximizing Bayesian properties.
So the question was different. We are testing this condition decision tree.
Yeah.
Do you also make use of conditional probabilities?
They are conditional probabilities. Absolutely. What is the probability of class A given income is this, age is this, and this is that? That is what the path is. Yeah, they are using a different loss function. So all algorithms do the same thing in different ways. If you understand this, you will not have problem in learning any algorithms. So decision tree is all the conditional probability. The path is the condition. Based on the condition, what is the probability of finding this class?
I don't know whether it's relevant or not. Can we do like that? Let's say 0, 1, 0, 1 we have. Can we predict whether the next value will be 0 or the next value will be 1?
What do you mean by that?
And this is the sequence, like regression follows the sequence. What is the pattern of the data?
Yeah.
In that way, it says, let's say the next value will be, there might be a possibility that the next value will be something, whatever it is.
Mm-hmm.
Can we do in that way? Like let's say we see 1, 0, 0, 1, 0, 0, 1. This is the pattern going on in some data, and we will run a prediction model. Can we predict the next value?
Predict what's the next value going to be.
Seeing the pattern of the whole. Like in 10th or 12th exam, we see 8, 2, 8, 9. There is a pattern inside it, let's say. Can we do it that way?
Only if you see a pattern, you can build models. If you don't see any patterns, you can't build models. He brings me back to one more very core issue, very core point that you need to be aware of. We build models only when, this process P, it takes as input something and output, This output that it generates, this output should be, usually it's, say if it's a numerical value, it should have some kind of a distribution. The distribution will have a central value and some spread and so on and so forth, the characteristics of distribution. Only when you have well-behaved, well-defined processes like this, whose outputs have some well-defined shape, in terms of the center values and the spread, only then we can build models to represent this process. If the output of this process is going to be random in nature, we don't know what it's going to be. Sometimes it's 10, sometimes it's 40, sometimes 9 random outputs. We cannot build a model to represent this. You can build models only for those processes which are well-defined processes. So coming to your requirement, if the output, the 10010, whatever you're seeing, it's an output of some process. If the process is outputting this in some patterns, the pattern could be in form of Gaussian distribution, so on and so forth, only then you can build a model to represent that process and predict what's next value going to be with some confidence levels. You can't model a random process. If that 1001 and all is coming out randomly, then you can't build any model. Yes?
I understand what is the PA with condition A, right? The standard formula is called. So now we are actually calculating PAB by putting PBA condition. So yeah, we are getting an output, but what is the need of doing that? Is it that previous numerator values is not calculatable or?
No, you're depending on past data. What is the probability of now a patient walking into my dispensary? I want to classify him as, does he have benign or malignant, cancerous or non-cancerous? Instead of building a model which is where input is the attributes of the patient and building a model to predict that, go back into your data set of the past patients, those who were cancerous, how many of them had these conditions? If majority of them had these conditions, then likely this guy is going to be cancerous. If the past data shows that amongst cancerous patient, this kind of attributes was very low, then maybe he will not be a cancer. So I flip the argument and go back to my past data and see what is the likelihood ratio given the past.
We can do same thing in this prima case, because here also what we are saying is.
That's what you're going to do, correct? That's what you're doing here. That's what you're doing. So shall I get in the hands-on? Okay. It's the same data set. So all of you know what the problem is. Okay. We have the wine data sets, this thing, but we can do this on. Would you like to take this as homework? Apply this Naïve Bayes algorithm on PIMA data sets and see what is the result. You have to give me overall accuracy and class level accuracy. Right? All of you okay? Would you like to give it a shot? Okay. Then let's go through this wine data set. Naïve Bayes wine. Okay, this data set has come from Italian wine brewery, wine farm. Okay, this is a real data set. Apparently, there are 3 different.
Wine data set. We don't have it. We don't have wine data set. That wine.cs.
You don't have data set. Okay. Don't worry, I'll pass it on to you. It's there on pen drive. She'll pass it on to you. This is wine.csv, not red.
Some people it's well, some people it's not.
But you can try it on red also. It doesn't matter. They're the same. This thing. Source is the same. All right. Now the requirement is there are apparently 3 different classes of winemakers. Okay, and the situation is the way the wines are classified. I wonder if you people know how it's classified. You have specialized, skilled people who actually taste the wine and they give the classification, the quality of the wine. Yeah. So this is one of the most unenviable jobs, or rather enviable jobs, where you get paid for drinking on the job, right? So the requirement is, can you build using data science a model which takes as input the various parameters of the wine and it tells you what the class of the wine is going to be. So I can replace these people with automated systems. That is the objective. Okay. So if you look at the data set, these are the columns available in the data, which I have noted from that UCI data set. The cultivator, alcohol levels, malic acid, ash, alkalinity. Honestly, I have no idea about these things, but these are the various parameters available. So when I load this data set and do a df describe once again is used to identify the tails. Look at any of these columns. We'll just look at one. Take your, okay, look at this, interesting. Look at the cultivator is a categorical variable, so don't look at that. Look at alcohol, mean is 13, median is 13. Malic acid, mean is 2.3, it's almost 2. Ash 2.3, 2.3. Alkalinity 19.49, 19.5, almost same. So every attribute, the mean and median are almost coinciding. So there is that, to that extent we are safe. Look at the tails. This tail is, sorry, start with this. This is almost 1 unit. Yeah, it's 1 unit, and the left hand side tail is also 1 unit. This is 2 units. This is almost 2 units. This is 2.5 to 3.5 units. This is 1.3 to 2.2, almost 5 plus units, 0.7 units. Every dimension, mean and median are coinciding, and the tails on the both sides are almost equal size. So looks like most of the dimensions, there is not much long tails or skews. Only one dimension you will see, which is magnesium. Mean is 99, this is 98, a difference of only 1 unit. Central values, no problem. Look at the tails. 10 units. Sorry, this is 18 units. 18 units versus 55, 54 units. Yeah, this tail is very long compared to the left hand side tail. So this is when your central values are overlapping, 98 versus your 99, central values are overlapping, very small shift. That means you have only a few outliers, very few outliers on the right side. Otherwise, the mean would have been drastically pulled to the right side. So 1 or 2 records seem to have outliers on that one particular dimension.
So should we go ahead and
All outliers have to be handled.
and then move like
Replace them with some different values. Dropping records is the last option. You may have to, but it's last option. The visual way of seeing this is pair panel, and this is the pair panel. I'll come back to this code. I'm looking at the data types here, but I'll come back to the code. Look at the distributions, and I want you to compare this distribution with PIMA distribution. So let's compare this with PIMA, okay? There are 3 classes and hence 3 curves. And look at these curves. They are overlapping. They are overlapping, but you see the difference? What is the difference? Central values are separated apart. The means are not overlapping. And that makes a huge difference in your ability to distinguish the classes. In PIMA, the problem was even the central values are sitting on each other. So the body is significantly overlapping, but central values are separate. So we are in a better condition than we were in PIMA. Look at this column. The blue and the orange are overlapping, even the central values are overlapping. But at least the green is away. So all the columns, this is, I think this is the worst column we have. This is in your data sets, where all the 3 columns are absolutely sitting on top of each other. This one. And this is ash. Okay. Ash, all the columns, all the classes are sitting on top of each other, including the central values. However, because I have other attributes which can help me segregate, I can ignore this, right? There you go. So in many of the dimensions, two classes are overlapping, but as long as the third one is away. So this is what I was saying. If you have a dimension in which the two classes are significantly overlapping, small change in shift, but when I combine this with another dimension, the two Gaussians, they become linearly separable. So I'm seeing this distribution this way, I'm seeing this kind of overlap. I'll redo this. I'm seeing this kind of overlap. When I use another dimension, in the other dimension also I'm seeing an overlap. But when I put them together, in that mathematical space, the two Gaussians become linearly separable. Because of that, linear separability now possible amongst the classes on the dimensions. Look at this dimension. This one, I don't know which one is this. This one is not going to help you separate the orange from the blue. Doesn't matter, as long as I have this dimension with me, which separates orange from the blues. So one dimension will compensate for the other dimension. So overall, these weak predictors put together become strong predictors. Exactly. Overall, these weak predictors put together become strong predictors, and as you will notice when you go down the line, let's look at the data types. We don't have any non-numerical columns here. Everything is numerical. Keep in mind, all algorithms need numerical columns only. Numerical columns could be categorical or real numbers. Come down. So I'm separating out the X variables, independent variables. The target is the cultivator. I'm splitting my data into training set, test set. I'm splitting my data into training set, test set. Yeah, are all of you with me on this? Okay. You can actually download the dataset from UCI if you wish to. This dataset you can download from UCI and run the code. Very good. I'm instantiating the Gaussian Naïve Bayes here. There are different variants of Naïve Bayes. This Naïve Bayes assumes that the dimensions are Gaussian on each one of these, the distributions are Gaussian on each one of the dimension, and we meet that requirement very well. On all the dimensions, the classes are distributed in almost Gaussian ways. Gaussian means looks like normal distribution. So a perfect case for Gaussian Naïve Bayes. So I'm calling Gaussian Naïve Bayes here. There are other variants like multinomial Naïve Bayes and other Naïve Bayes which you can make use of. So I'm instantiating the model here. I'm going to do the model fit here. This is where our Naïve Bayes likelihood ratios will be calculated. And then I look at this. On the training set itself, I'm doing a testing. It's giving me 97% accuracy. Why am I doing this? I'll tell you in a minute. While I can also do this model on the test data. Here I'm running the model on the test data. Okay. And in metrics, there is a function called classification report, which gives me all these metrics, recall, precision, everything in one shot. If you're interested, you can separately print the matrix also, confusion matrix. Now look at this confusion matrix. Look at this. Look at the class level recall. Look at the class level recall. Any problems? Hey, Mohli, any problems? From SQL and import Gaussian. Okay. All right. Now look at this. There are three classes here, 1 to 3. And look at the class level recall. What is class level recall? Accuracy at class levels. Almost 100%. 1 means 100. 95%, 100%. So each one of the classes, it's able to accurately classify with a degree of, this is what we wanted in PIMA diabetes. is giving us accuracy in wine data set. Okay, I'll talk about this micro average and all these things down the line. We'll talk about this later. Right now, just look at this recall matrix. I've not told you what precision is. And look at the confusion matrix. Actual number of class A in your test record is 23. All of them have been classified as class A. Actual number of records for class B in your test data is 19. It has correctly classified 18. 12, it has correctly classified 12. You are able to achieve this kind of a score in this model, even though the dimensions are overlapping, the classes are overlapping on all the dimensions, because of some dimensions which come together to make strong predictors. So you should understand the difference between PMA diabetes and this. In both the cases, the classes are overlapping, but there's one very important critical difference. And it's that difference which is making this. Right? So you can run the same algorithm, Naïve Bayes, on PMA diabetes and see what is the score you get there. Your job here is to select the right attributes.
But here we are not giving the all
That this is, you will never get data on a plate when you're doing real life projects. This is only classroom. But when you do sit down and do real life projects, your customer says, suppose a simple example, can you use data science to improve my customer CSAT rating from the current 3.5 to 4.5 out of 5? Can you do something using data science to help me improve my customer rating in my technical support? These are the kind of requirements which will come to you. Data will never come to you. So now your job is CSAT rating, customer rating for technical support. What kind of data you need? Not decide. You have to first guess what kind of data I need. Your domain expertise will help you. If you don't have it, you'll need to have domain experts. So for CSAT rating in customer tech support, what kind of data I'll need? Can somebody go back to the past tickets? Okay, go back to the past ticket. What kind of data you need? Go back to the past tickets. From the past tickets, you collect what kind of ticket, P1, P2, P3 tickets. I need to find ticket classes. Then whether the ticket belong to hardware, software, or something else, I need those things. And various other, you will decide what kind of data you need. The next challenge will be, where will you get the data from? Some data will be available within the organization. Some data will be available outside the organization. Some data will be available with the customer. So getting these stakeholders to give the data to us will be such a challenge. So all your soft skills will come into play. Right? So once the data comes in, you have to first establish the reliability of the data. What if the tech support department has given you data where customer is very happy? They have not shared with you the dirty data. Your model will go for a toss. Those are the challenges which you will face as a data scientist. Once the data comes to you on those various attributes that you have, you will do this analysis using pair plot and other techniques. Is this column good or that column good? Which column should I use to define customer satisfaction? I come from the IT world just like you do, many of you do. We people have done a lot of projects in Java and C and all those things. The project starts with customer requirements, which we turn into technical requirements, that we turn into design requirements, that turns into code specs, coding requirements, that turns into unit testing, integration testing, and finally, then we go for acceptance testing. In acceptance testing, usually it bombs. Right? The reason why it bombs is, we look at data only in the last stage, where we come to acceptance testing. We ask customers to give us some data. In data science projects, your project will start with data, the project will end with data. Data is the core, you will be revolving around the data sets. So 80% of your effort, estimated effort in data science project, you will see that when you do the capstone project, will go in getting the data itself.
So it's usually start with data-driven approach and end with
100,
data-driven
100%.
and end with data-telling stories.
Yes, 100%. Visualization and storytelling from the data. That is what data science is.
So in between that data analysis.
In between the data analysis, feature engineering, feature selections, model tuning, all these things come in between. Hey, so please don't make this assumption. In this hands-on exercise we are doing in the class, you're getting all the data from, right? This will not happen in real world. That's why when people come and do capstone projects, many of them want to do self-driving cars. So we have to take them out separately and tell them, hold on. At least a decade of research has gone into building those self-driving cars. You can't do it in 4 months. So when you come to capstone project stage, you're very far away from that. Please sell it to capstone projects with care. Right, guys? Okay. What I'm going to show you is one more thing. Okay. Though this is kind of doing very too early in this for you, but still let me do it. When you build these models, okay, we need to understand how the model is likely to perform in production. Because I'm going to put the model into production, which means I'm going to disrupt many of the processes in production. So the stakeholders in production are going to ask me, what is the performance you expect from this model in production? Suppose somebody asks you this question, what is your answer? Okay, it completely matched with this, what I'm going to cover, because how do you prevent this from happening in production? So when somebody asks you this question, what is the performance you're likely to have in production? We never give point estimates. We never say my model is going to give 78% accuracy or 80%. We always give a range estimate. My model is likely to give me accuracy between 80% to 95%. The moment you give range, that means you're not 100% sure. The moment you're not 100% sure, statistically you're supposed to associate with a confidence level. How confident are you in this range? So usually the confidence level is measured at 95%. So we give a confidence level of 95%. 95% confident that my model is going to give me accuracy between X and Y. But to be able to do those things, find the 95% confidence level for your estimates, we use a technique called bootstrap sampling. In statistics, it is known as sampling with replacements. Okay, and we also use a technique called k-fold cross-validations. So I'm showing you this k-fold cross-validation, what it means, but we'll do this in detail down the line. Look at this. From Scikit-learn, import cross-validation score and cross-validation predict. These two functions are available already. Let me explain to you first what is cross-validation. I have this data set with me. Okay, suppose k-fold CV, that which I'm going to use, k stands for an integer number, just like k nearest neighbors, an integer number. Suppose I say k is equal to 10. Usually we take 10 as reliable. What it's going to do is, it's going to break your data into 10 pieces, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. It's going to break your data into 10 equal pieces. Then what it's going to do is, for I equal to 1 to 10, where I is an index, I equal to 1, 2, 3, 4, 10. For I is equal to 1 to 10, fit using 9, test or predict using the left out. So first time when I is 1, it'll take some 9 data sets, do the fit, and it'll test on the left out. Then when I becomes 2, it takes some other 9, maybe this 9, do the fit and do the left out. Then it'll take some other 9, do the fit, left out. It'll do this 10 times because you have taken 10, k is equal to 10. Because you have taken k is equal to 10, it's going to break your data into 10 pieces, train on 9, test on 1. And it'll do this 10 times. train on different 9s each time, test on a different left out each time. When you do this on this particular data set, so I've imported these two. Cross-val score, I've supplied the model to it, the model which I built up, the training set test label, and CV is 10. When I do this, look at the scores I'm getting. First run, it gave me overall score of 92.8. Second run gave me 92.8. Third run, it gave me 1, 1, 92.3, 92. This is all the scores you have got. Average of all these scores is 96.12. So you can expect your model in production on average to give you 96% accuracy. However, we want to give a range. To get the range, you can find out this distribution, 95% confidence level of this distribution, or resort to bootstrap sample. We'll talk about that later in detail, right? So we make use of this technique to find out overall how the performance is going to be in production. 96% average accuracy score I can expect from this model on this data set.
In this model, when we do model scores, we did train set and train
Yes.
right? And we got accuracy of 97%.
On the
train set. Do you think this accuracy is not correct? Because we have.
No, I'll tell you why we did that. No, we did subsequently testing also we did. Look at the line, we have done on testing also. Okay, why did I do the evaluation on training and testing? Let me tell you this, okay? With that we'll wind up. This is a very important point, and you should learn this trick now itself, and if you reflect all these things in your projects, it'll be good. Oh, there it is, okay. Remember we talked about overfit, underfit? Okay, what is underfit? How do you define underfit? Huh? Sorry? Loosely coupled with less dimension. Straight line, curve line, what the hell, hey boss? What is going on? Using what? I want to reach a sweet spot. On the left side is low, underfit. On the right side is overfit. But how will it know whether a model is underfit or overfit? Okay. Guys, let's. Very good, thank you. Huh? Hey, no, enough. Underfit is that case where in training set, accuracy is very high. Okay, I'm sorry, accuracy is very low, and in test set also accuracy is very low. Overfit is that case where in training accuracy is very high and testing accuracy is very low. All right, right fit, this is overfit. Right fit is that case where training accuracy is equal to, more or less equal to test accuracy. All right. So if I plot a graph of errors, okay, and this is my complexity, then you will see that my training error comes to 0. Especially decision tree will give you training error 0. But this is my training error. I call it training error, TRAINING error. As my complexity increases, training error comes to 0. But you will see that this is my complexity, okay, I'm increasing complexity in this direction. You will see that the test error is usually higher than the training error. It also comes down, but after some time it deviates back up. you'll notice that the test error also comes down to some point. After that, it backs up, it peaks up. This difference, okay, this difference where the training error starts deviating back up, you should stop here. Below this, it's underfit. Above this, it's overfit. In this situation, your model has absorbed all the noise in the training set and become very complex. And when you take that model on the test data, it bombs. Error is very high on test data. Okay? So this point is what you want to check. So whenever you build model, run the model both on training set and test set. If on training set and test set, training is 80% accuracy, test set is 60% accuracy, you are in this region. If training set and test set, both of them are similar to each other with very few difference here and there, then you're probably in this region. Training is also poor, testing is also poor, you're in this region. Underfit region. Oof. So much to discuss. I know it becomes a bit of overwhelming with so much of information coming in such a short span of time. It'll take time, don't worry about it. Take time, take your own time to sink all this in and keep practicing on the UCI datasets. But don't get miscarried by the UCI datasets, as Birendra pointed out. In reality, you'll never get such datasets readily available. Never. If you get, you have to suspect it. Okay? That reality will hit you when you do the capstone project itself. The idea is to teach you that reality. All right, so I'm going to stop here. I'm done for the day. Any questions, feel free to shoot. We're stopping a bit early today, but yeah, that's, yes.
You explain the pair plot and what are the inferences we can do?
Pair plot? Yeah, sure, why not? We can do that. For this data set? Okay.
Actually, I have done this project based on that
Scores have gone down, right? Overall, what is accuracy?
77.
Overall accuracy. Yeah, that is what 76.
Overall 74, the training set is 74.
That's okay. 74, 76, that means it's an underfit region. Both of them are very close to each other. And class level accuracy, diabetes class, recall, what is the recall? Hey, diabetics class, 88. 62 for diabetic class is 62. 55% and 62% is a big jump actually. It's a big jump. So for diabetic class, this Naïve Bayes is doing well because, can you tell me why Naïve Bayes is doing well for the diabetic class?
You told multiple, if it's overlapping, maybe the different
Weaker or weaker will go.
In diabetic class, in PIMA diabetes data set, you notice that there were 3 attributes on which there was a very small separation between orange and the blue on the 3 dimensions. Those weak predictors are helping the Naïve Bayes algorithm over there. Right? So the lesson that we have from this is, which we'll revisit tomorrow anyway, given data set and given problem statement, we never rely on one single algorithm. We always build multiple models. Each model might be different algorithm, and then we average out. That concept is called stacking. If you use the same algorithm, multiple instances, that we call ensemble. So in production, we always put an ensemble or a stack, and the ensemble or a stack will give you a much more reliable result than individual instances will. Okay, let's move on. So let's see this pair plot. There you go. For always first look at the diagonals. Okay. In the diagonals, the first column is the category, the target column. So we can ignore this. This is category of the 3 cultivators, people who cultivate. The next column is the alcohol. Look at the diagonals. This is alcohol versus alcohol. So it makes no sense to give you scatter plot here. So instead, they have given you density distribution on the alcohol dimension. Since we have used this hue color, which means give me separate colors for separate classes, it's showing you the 3 classes. And what is coming out of this is, between classes there is overlap. But fortunately, the central values of these classes, they are not overlapping.
So that is basically alcohol versus cultivator.
No, this is alcohol versus alcohol. This is just distribution of the classes on alcohol, univariate. This analysis is univariate analysis. It's not comparing the dimensions.
But we are given U is equal to cultivator.
So it's giving you a distribution of cultivators from class 1, class 2, class 3 on this dimension. How the values of alcohol for class 1 is distributed, how it is for class 2, how it is for class 3. So what this is telling us is the alcohol dimension can be used to separate out the 3 classes. Okay, go to the next one. If you observe carefully, malic acid, what it's saying is the class 1 is distributed like this, the class 1 malic acids are distributed like this, class 2 malic acids are distributed like this, and class 3 is the green one. What we are seeing is outliers here. For the blue class, on this particular dimension, there seem to be outliers. You see a small bulge over here. Similarly for orange also we are seeing bulge. The problem we are seeing for the green one, there seems to be huge range on both sides. Yeah. So green one also seems to be having some extreme values on both sides. That's why the distribution itself is stretched out. So I have to go back to the records and see on this malic acid for each class, what is the problem? What are these outliers and need to deal with it? But right now, in the raw form, the green stands out separately from the orange and the blue. But the orange and the blue class are overlapping. So this dimension may be very useful in separating out greens, but may not be very good in separating out orange and blues. This dimension is your ash. It's relatively the most useless dimension in this set.
Malic acid, you have the outlier. Suppose if you take the outlier, so you have very less spread. It means that it's a very good predictor for the blue this data.
No, the predictive power is a function of how cleanly these separate out the distributions. The predictive power of a dimension is a function of how cleanly these distributions are separate out. Suppose there was no blue class. This is a very good dimension to separate orange from the green. If suppose there was no green class, this is a weak predictor for orange and blue. This ash, it's a very weak predictor for all 3 of them. Okay. This alkalinity, if you see, if you look at, if suppose the blue class was not there, then we are in Pima diabetes case. But at least it's a good separator for green and blue. Right? So individual dimensions may be weak predictors, but when I put them together, they might be able to segregate the 3 classes properly. And that is what is happening in the dataset. You asked the question, right? How to interpret this? That's what we're doing. The scatter plot makes no sense because we are not building any linear models here. Okay. So scatter plot I'm not referring. So diagonals is important for us. Any other question?
Based on this, we can drop the variables which are less important.
100%. So, but maybe by dropping that ash dimension and reducing the cursive dimensionality, I might be able to get more than 96%.
So if you drop the ash and again read the bottom,
I don't know. I've never done that, but you should try it. Maybe you will get it. Handling the outliers might help you in classifying, because outliers, hey guys, all of you this side please. All of you this side. This is a Gaussian Naïve Bayes. Gaussian Naïve Bayes expects your data to be distributed like this. But wherever your data distributed like this, if you handle these outliers, you might get better results, right? So if you handle the outliers, both logistic and Naïve Bayes will give you better results. Because outliers increase log loss in your logistic. So if you handle outliers, both logistic and Naïve Bayes will give you good results.
But if the first leg will come after like one standard
Treat it means?
that's really great.
You're talking about outliers. Okay. Don't remove the outlier. Don't drop the records as much as possible. Unless you're lucky guy, you're given terabytes of data. Right? So usually you'll find yourself in a situation where we don't have the luxury of dropping the records.
But in case of breast cancer and all, we don't know the cell radius. If we replace it with median values or something, that's domain specific.
You have to take, yes, good point. You have to have the domain expert with you to tell you whether calculating the radius is prone to error or the perimeter is prone to error. Right? Because there is a strong relationship between perimeter and radius. That's why you're saying that. So it depends on the domain expertise you have. All right. Okay. There's one point which I wanted to say. Okay. This is called data leaks, and guys, with this I'm going to stop. I'll not go beyond this. Be careful about data leaks. I'll tell you what data leaks is. In your exams, if the question paper gets leaked out, obviously we'll score very high. Right? But we might not have the real knowledge with us. Same thing can happen in modeling. So in modeling, we break our data into training set, test set, right? And we build our model, model dot fit. We do this using training data. There are various ways in which the test data can leak into the fit function. One of the simplest way you can do this mistake is where you first take the data, you convert this data into z-score, and then you split this data into training set, test set, build your model on this. Why? Because z-score is xi minus x bar by standard deviation. Xi minus x bar by standard deviation is a z-score. This standard deviation is a result of all the records put together. Right? Now, when I break this data into z-score data into this, the test data has already been influenced by the training set. But the test data in no way should have been influenced by the training set. They are not independent of each other. This is a very common source of data leaks. In the classroom, it's okay, but you cannot do this in your projects. Then what will happen is, your model will perform well on test, but it will bomb in production. That is one very common way of data leaks. So whenever you do transformation of your data from raw to this, if the transformation involves all records put together to find your standard deviation, something of that sort, don't do that. Always break your data into training set, test set first, then do the transformations.
I think we did this for this.
Which one?
First Python notebook which we did. Right?
We'll do this mistake in entire all the Python notebooks. But you please be aware of it. Don't do this in your projects. The second thing I'll tell. Second problem statement is, we talked about one-hot coding. We talked about one-hot coding, right? Look at this. You have in your data set a gender column which has male, 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 females, females, okay, males. Always convert the one-hot coding first so that it becomes gender male, gender female. This will become 10101001 1 0 1 0 1 1 0 1 0. Okay, all of you got it? Then you break your data into training set, test set. This is okay. Training, test. The reason why this is okay is this record has not been influenced by any other records. The records don't influence each other. The transformation of records from here to here is independent of other records. So this is okay. Okay. If you do this transformation after breaking your data into training set, test set. I told you in Z-score, you first break your data into training set, test set. Okay. Then first do Z-score on training, then do Z-score on testing separately. If you do this one-hot coding after breaking your data into training set, test set. Now I break this into training set, test set. What's going to happen is in your training set, you're going to have only one column, GM, 1 1 1. In your test data, you're going to have two columns, GM and GF. This will be 0 1 0 1 1 0. So your training data and your test data will not match in terms of the attributes. So whenever you're doing transformation, if the transformation is something which is done record-wise, do it first, then break your data into training set, test set, especially one-hot coding. Otherwise, you'll end up in runtime problems. If you're doing any transformation which involves all the records put together, like calculating standard deviations, then first split it, then transform it. Otherwise, your data will leak.
Here, number of observations will get changed.
Second most take
One-
it to
one-
this score.
getting it to two.
Score and
Yeah.
test to
Is there any effect of this? Any kind of bias?
Yes, you are. The moment you add dimensions, you're going towards higher complexity of your models. So you're decreasing the bias error but increasing variance errors. So if you create one-hot coding out of a column where the cardinal values, the distinct values is 50, you're going to end up with 50 new columns. So imagine from lower dimensional space, you're going to such a high dimensional space and your data points is also not very high. You'll end up with a very complex model. So you'll end up in overfit zone, variance errors.
So why we need this? We can still segregate, we can still use 0 1 as the value for.
Algorithm will think that 1 is greater than 0.
Here, if we have three categories, A, B, C, and we do level encoding first. So it will convert to 1, 2, 3. In this case, it might think that C is a higher
It will.
priority than C.
It will.
So what we'll do on
On
whatever.
Yes.
Now it will convert to 0, 0, 1, 0, 1, 0 as per the sequence. So in this case, if we drop one of the variables, the variance will also decrease, and we can predict that if it's 0, 0, then maybe that variable will be 1.
Yeah.
So we can use that way also to reduce the variance.
Yeah. Okay. One last point. Last test point. This we have been saying since last 3 points. Whenever you create one-hot coding, for example, in this case, you are creating collinear columns. Columns which influence each other. The presence of 0 here tells me that this column will be 1. So I'm able to predict the value of the other column based on this column. So you're introducing collinearity over here. To address this collinearity problem, when you create one-hot coding, we may drop one of the columns. So 0 means male, 1 means female. So I get that information from here itself. I don't need this. So when you do one-hot coding, you're introducing multicollinearity. When you bring multicollinearity, you know what problems exist, what problems happen, you know that. So we might have to drop some of these one-hot coding columns to remove the multicollinearity. We do that.
Again, it has 0 1. Again, same issue. One is higher.
The purpose of one-hot coding is.
One-hot coding does not introduce any order. It just stores it as a label, 0 and 1.
So we can also convert the gender column as the category column at 0.
Unfortunately, when you do that, when you use pandas data frame categorical function, it actually says that it is ordinal values. It has order in it. Discuss the steps and then we'll move on. We'll use a new data set on which I'll run KNN, regressor, then linear regressor, and we'll compare the two.